Welcome to Mode Concept. This is the practical approach to systems hardware design. In this course, we have a lot of labs to complete. But before we go into these labs, it will be good to understand what systems hardware design is. So let's just have a brief overview of systems hardware design to give us an insight into what we need to know. Let's just use biology to explain a little thing here. A cell in biology is seen as the unit of life. The same way in electronics, the gate is seen as the unit of systems hardware. A group of cells in biology form tissue, a group of tissue form organ, system, and so on. The same way in our electronics, a group of gates form hardware chip. A group of hardware chip form systems hardware. Now, these logic gates are like switches that opens and closes under certain conditions. They are the building block of all digital electronic circuit and microprocessor based systems. The AND, OR, and NOT have the basic logic gates because of the fact that other logic gates are formed from them. When you add a NOT to an AND gate, you form a NAND gate. When you add a NOT to an OR gate as well, you have a NOR gate. This NAND gate and NOR gate are known as the universal logic gates. Every other gate can be formed from these two gates. That is why they are called universal logic gates. These logic gates have states. As we said earlier, that they are like switches. So switch can be either on or off. But in logic gates, we see them as 0 or 1. Based on Boolean logic, you can have it as true or false. Then, as voltage state, it can be high or low. As voltage level, it can be plus 5 volts or 0 volts. So looking at the Boolean algebra and voltage level here, we represent 5 volts with 1 and represent 0 volts with 0. So we'll be talking about 1 and 0 all through our lab. When we talk about 1, that means 5 volts. We talk about 0, that means 0 volts. So let's look at the logic gate. Now, the NOT gate. When this switch is open, it represents 0. When this switch is closed, it represents 1. When this LED is off, it represents 0. When it's on, it represents 1. So from this symbol to when this input is 1 here, the output is 0. And when the input is turned to 0, the output will become 1. So let's quickly look at this circuit in Pro Tools to see how the simulation runs. Let's quickly go to Pro Tools. This is Pro Tools now. I'll quickly go to schematic capture to start a new program. Pick my components. I'm going to pick a NOT gate. Logic state. Logic probe. Switch. I'll pick a LED again. LED. Red. I'll pick a battery. Battery. This single cell battery. So I'm going to work with this now. So let's start with the electrical wiring diagram. I'll pick the battery. Switch. I'll close the switch because it's not the main switch. The main switch This is the main switch we are interested in. Let's do the work for us. So let's do the symbolic representation before we run the simulation. So now I'm not going to break up the truth table here, since we know that when the input is 0, output is 1. When the input is 1, output is 0. So let's just have it in our head. I'll just go to simulation now to run simulation to verify this. So you see, so when the switch is open, it means 0. When the switch is closed, it means 1. When this LED is off, it means 0. When the LED is on, it means 1. So let's see what happens now. When the LED is 0, output is 1. And when the, okay. So I'll increase this to 3 volts, this voltage, because 1.5 volts cannot light the LED. 2.0 volts. So now let's run the simulation and see. So now let's run the simulation. The switch is open, and the switch is 0, output is 1. The input is 0, output is 1. The switch is closed, and the switch is 1, output is 0. Input 1, output 0. So this is just how the NOT gate works. You can see from what we have here. This is what we just had in that our diagram. This diagram. So that is how this thing came to be. So if you look at the OR gate, this is equally the same thing. If you see run this on Pro Tools, you will understand that this is how this man operates. The OR gate. The OR gate just performs logical or operation on 2 inputs or more. So now let's just look at this example with 2 inputs. This is a wiring diagram of an OR gate. This is the battery. So when this switch A is open, it means 0. When it is closed, it means 1. Same thing is applicable to this B. And you know how the OR gate works. When both inputs are 0, output is 0, then the rest of the output is 1. So the same thing is applicable to this man. When any of this is closed, there will be an output here. When both are open, no output. So both open, 0, 0, nothing. But when any of them is closed, something here, that is 1. So that is how the OR gate is. So if you see run this on Pro Tools, you'll understand what I'm talking about. So let me pick OR gate off. So this is it now. As we said earlier, is the OR gate. When both inputs are zero, the output is zero. So for other conditions, the output is 1. So let's go and see. Let's simulate now. So now let's simulate. When both inputs are zero, the output is zero. When both inputs are zero, the output is zero. You can see that. So when any of these inputs is 1, the output becomes 1. So let's start with this. You see, output becomes 1. Output becomes 1. 1. So this one, output is 1. Output is 1. Output is 1. So this is how the OR gate is. I'll stop simulation and continue with the AND gate. So this is just for the OR gate. Then the AND gate. The AND gate equally performs logical AND. The AND gate performs logical AND operation on two or more inputs. So let's look at the wiring diagram of the AND gate. This is the wiring diagram. These two switches must be closed for you to have an output. That's how the AND is. It's only when the two switches are closed, 1, 1, you have an output. The rest of the conditions, no output. That is, output is 0. So let's rush to Pro Tools and run this to see what we have. To see how the wiring diagram is organized, is arranged. To see how the wiring diagram is. So now let's quickly edit this to form an AND gate. So this is switch A, switch B. This is the output. So for AND gate, let's get the AND gate symbolic. The AND gate chip. And I'll just replace here. Replace. So good. So let's just run the simulation and see what we'll have. For AND gate, it's only when both inputs are 1 that you have an output. The rest of the conditions, no output. So look at it here now. This is the two inputs, A and B. 0, 0, no output. 0, 0, 0, no output. That is output 0. So 0, 1, nothing. 1, 0, nothing. Then 1, 1, output. So let's look at this wiring diagram. 0, 0, nothing. 0, 1, nothing. 1, 0, nothing. Then 1, 1, output. So this is just for the AND gate. So let's continue. So the NAND gate is just adding a NOT to an AND. You have a NAND gate. So this is just how the sketch is. If you run this on Pro Tools, you probably realize this, and this is how this one is. So this is just the NAND gate. For the NOT gate, you just add a NOT to the OR gate. This is how it is. Just NOT the OR gate. You have a NOR gate. This is equally how the chip is, and the output is equally this. So that's the NOT gate. Then, so All the digital ICs, all our digital chips, as we said earlier, depends on gates, few basic gates. You see, so the way they are interconnected, the way the gates are interconnected inside the digital IC, that means how that IC is going to be classified. So there are different classes of IC based on the logic family they belong to. So, so let's look at logic families. We have the bipolar family, the MOS family, and the hybrid family. But our interest in this course is on bipolar family. So let's quickly go to bipolar family. In bipolar families, we have the diode logic or the diode resistor logic. This particular family uses diode or diode and resistor to form the logic gate. So it can be an AND gate or gate. So you have the resistor transistor logic. This makes use of resistor and transistor to form the logic gate. We have the diode transistor logic that makes use of diode and transistor to form the logic. We now have the transistor transistor logic that makes use of transistor and transistor to form the logic. Then finally, we have the meter coupled logic, which is the only transistor but coupled in a different, as in configured in a different mode. That's what we call it a meter coupled logic or current mode logic. So in this course, we have the following labs to complete. We will design the diode resistor logic. We will design resistor transistor logic. We will design diode transistor logic. We will design transistor transistor logic. And finally, on the designing, we'll do emitter couple logic. Then we'll now go over to construction. And the construction aspect of it, we'll do the construction of all these things we have designed. We'll design all these ones on Pro Tools. And after designing them, we'll now go to use our breadboard and VeroBoard to construct all of them. So we'll do their different gate types, whether OR gate or AND gate or NAND gate, as the case may be. So when we have covered this, that means we are done for the day. So thanks for watching this overview and following me closely. Do well to like the video and subscribe so that as the labs keeps dropping, you'll be catching them as they are dropping. Thanks for watching. Goodbye.